Do time-correlated multi-domain analog, digital, and RF signal analysis that's enabled on our new oscilloscope platforms, and talk about some of the ways you might be able to use that. So I'm going to generally be heavy on demonstrations and light on slides. That's typically what I like to do here. But all of this is we're going to be talking about is enabled by some new ASIC technology that we've developed for our latest oscilloscope platforms that gives you some very unique capability in terms of looking at analog, digital, and RF signals all in a time correlated way on one platform. This one slide just kind of shows some of the platforms that this new hardware capability is built into. We're going to be focusing a lot on the performance of the 6B series MSO that's over here on the right-hand side. It's a 10 gigahertz scope platform with up to 50 gigasample per second sample rate. And we're going to talk about some of the common features amongst this set and really focus a bit more on the RF capability. So all of these new scope platforms feature something called FlexChannel inputs. FlexChannel inputs means that any one of these inputs can be configured a number of different ways. It's the traditional Tektronix VPI connections that gives you, an analog channel that can be displayed in the time domain, frequency domain, or both. And we'll talk about what I mean by that in a moment. But there's also a feature that allows each channel to be turned into an 8-bit digital channel. And I almost hesitate to use that term digital. We actually call this probe down here a TLP058, a logic probe. But the reality is it goes much deeper than that. You can think of this probe, if you will, as 8 1-bit comparators, each of them with an adjustable threshold of plus or minus 40 volts on a line-by-line basis. So you don't have to just be looking at logic or digital signals. You could be looking at power supply pins, mode pins, discrete signals in your systems and things like that. And if all you need to know is when that particular voltage or node or mode pin or whatever goes above or below a certain threshold voltage, this logic probe is the way to do that. So it might mean if you need to look at the timing characteristics of numbers of different signals in your system, you don't have to burn a bunch of scope channels to do that. You could put 8 of those signals on one channel of the scope, and you can add more of these probes going down the line, so you can have up to 64 of these lines type of thing. So it may be to develop a complex trigger scenario, to trigger on a particular sequence of events and that type of thing. So it really goes far beyond just being a digital or logic probe. So I just wanted to kind of highlight that a little bit. Okay, so we're going to focus a bit on, on the RF capability today, RF and vector signal analysis capability as we kind of move forward through most of this presentation, but just keep this in mind when it comes to all this capability. Each of these channels can be configured by simply determining, by selecting what probe you're connecting to it or what mode you put that input in. And any combination of analog digital probes is supported on the scope platform, which gives you a lot of flexibility in being able to look at analog, digital, and RF and multiple signals in your system at the same time. So we're going to focus a bit more on the kind of advanced RF processing that we have, and it's a feature we call spectrum view. And spectrum view basically gives you a simultaneous time and frequency domain views of an input signal with independent acquisition settings in each domain, and I'll explain why that's important in a moment. You can control it much like you control your spectrum analyzer, center frequency span, resolution bandwidth, etc. And it gives you that time correlated view of your RF signal to other signals in your system. So I'm going to switch over and do a quick little demo of this, and we'll show you what we're talking about. Okay, so the signal that we're looking at on the scope here looks like a little wiggly digital signal. In this case, it's actually a spread spectrum clock. So if we want to look at the frequency domain content of this, we can simply go in and turn on spectrum view. And now I can see the spectral content of this signal. And I can go down to my spectrum badge here. The fundamental of this is sitting at about 98 megahertz. So I can dial in, say, 98 meg and hit enter there. And I'm going to knock the span down here to about 10 megahertz or so. So there's the spectral content of this spread spectrum clock. Okay, so nothing unusual, just is what it is. Now, traditionally, if you were looking at frequency domain content on a scope, you would be using something like an FFT, and we could do that too. But as you may know, there is some some difficulties in using an FFT, right? Because the FFT's result is going to be a function of what you set up in the acquisition parameters for the time domain. So for example, if I want this to I want to get this same view over here on my FFT, well, I can go in here, configure this view, and if I automatically, or if I go in and set the same span, say from 93 meg to 103 meg, like I have over here, I can dial in, say, 93 megahertz here and 103 megahertz here. But we can see that I don't nearly have the resolution that I have on the spectrum view. So in order to get that resolution, right, frequency resolution in an FFT is a function of how much time I'm grabbing in the time domain view. So I need to go in here and start grabbing more and more time. Eventually, I'll grab enough time here to get a frequency domain view that looks just like my FFT. And the problem with that now is that I've got the spectrum view that I want, but I don't have really good optimized settings for my time domain view. And that's typically the problem that you have when you're talking about using an FFT or a time domain view. You can't get an optimized view in both domains simultaneously. Because of the independent way that spectrum view works, you can get that. So let's talk about how that works. So this is what's kind of behind the hood, if you will. Here's the normal, typical signal processing path, very simplified for an analog scope. Right? So input signal comes in, goes through amplification, filtering, attenuation, etc., to our 12-bit digitizer. Those samples are then processed. You've got samples that go to the trigger system, and ultimately you put in waveforms in memory. What we've added with this is, in parallel with the normal time domain processing path, we're also taking those samples that are coming out of the ADC and making them available to a hardware digital down converter, much like what you'd find in a vector signal analyzer or real-time spectrum analyzer. So that hardware DDC feeds data both to the trigger system and into acquisition memory in parallel with the time domain data. So it's not an either or situation here, it's an and. You essentially get both of these put into memory at the same time. So you're acquiring out of the digital down converter baseband IQ data along with your normal time domain data. Everything is all time correlated, okay? And this gives you essentially a spectrum processing vector that we use to compute the spectrum from that is essentially independent of the time domain samples that you grab. So what you set up in spectrum view for things like center frequency and span are going to determine the IQ sampling parameters that get put in memory. Okay, and the 6 series scope gives you up to 2 gigahertz of RF acquisition bandwidth through this digital down converter. And this is available on every channel of the scope. So if you've got an 8-channel scope, you essentially have 8 digital down converters, and they can be set up to look at the same center frequency or different center frequencies and acquire data all simultaneously across all 8 channels. The controls, pretty simple. We saw this in the demo. You just double tap the channel badge, bring up spectrum view, and you can turn it on. You get up to 4 different spectrum traces. You also have some optional VSA traces, or what we call them RF versus time traces, to allow you to look at magnitude, frequency, or phase deviation over time. All of these scope measurements, pulse width, rise time, fall time, all the typical measurements that are available on the scope can also be used on these RF versus time waveforms. So you get some basic vector signal analysis capability. And it also enables triggering on the magnitude and frequency versus time traces. You can actually trigger on RF magnitude or even trigger on frequency changes, carrier changes, which is kind of unique in this scope. And I'll actually show you that here in a moment. Okay, so once you've turned on spectrum view, the controls for it, you get a little spectrum badge, and that again gives you your center frequency, span, resolution, bandwidth controls like you typically have on a spectrum analyzer or a vector signal analyzer. And this is where you can unlock the center frequency amongst channels and have set a center frequency on each channel independently. And you can also unlock something called the spectrum time. And now, as we'll see when we go through the demos, you can actually control where in time the spectrum measurements are being made. And that can be done in lockstep across all channels or on each channel independently. So we're going to go through and do a couple of different demonstrations here. The first we're going to do is looking at a microcontroller controlled synthesizer. It's controlled over a SPI bus. We'll actually be probing that SPI bus at some point, looking at some analog signals and looking at the RF signal as well. We'll do a couple of examples with this. And then we'll also do some more RF examples, kind of pulsed examples, one looking at phase differences between two RF pulses, and another that's looking at a frequency up conversion example, and see how we can actually utilize the ability to look at signals across multiple frequencies. So let's kind of switch gear. Let's kind of pick up where we left off here. I'm going to get rid of the math channel because we don't really need that. I'm going to literally, I can just drag it off the screen. And let's take a look at the RF versus time waveforms here. If I, again, double tap the badge here, go to spectrum view, and if I add my frequency versus time trace, I can actually see this is, again, I mentioned this is a spread spectrum clock. So it's a clock signal that is ramping up and down in frequency. We can actually see that characteristic down here at the bottom. But it's wiggling around because I'm triggering on the clock itself. But I can go in here and trigger on the frequency versus time trace itself. Okay, and you can see as if I close my trigger badge here, I can actually move my trigger level up or down and actually trigger on that frequency versus time characteristic, literally triggering on the baseband, underlying baseband signal on this this frequency modulated clock. And this is kind of unique. I only know of one other analyzer that can actually do that, being able to trigger on the baseband demodulated signal. So that can be really handy. Something else that's really handy here is that we can apply some of the advanced triggering to this as well. And what I've discovered with this signal on my board is that intermittently, it only happens once every few seconds, is that this modulation drops out. So what I'm going to do is change my trigger type from an edge trigger to a timeout trigger, and say if I stay low longer than, say, 100 microseconds, we'll turn that on here. I need to go and tell the trigger mode to be normal. And I'm going to go grab a bunch more data here. Actually, I just saw one trigger event there right now. Let's go grab another one. Here we just discovered this fact that this signal was modulated. You can see the modulation was all going along here, and then it went away and then ramped back up slowly. This is this is kind of a glitch, very, very tough to find, really tough to trigger on, but now I've actually seen it. And this also gives me the ability to show you how we can actually look at what the frequency domain looks like at different locations in time. You see this little yellow bar here. That yellow bar, we call it the spectrum time. That's indicating where this spectrum measurement is being made. I can move that anywhere within the acquisition. So I can see the spectrum look like over here where everything was clean. It was our normal spread spectrum clock. And then we can see when the modulation went away, we actually went down to basically a CW signal again, about 98.5 megahertz. And then eventually that ramped back up again, up to our full spread spectrum clock again. So being able to look at, once your acquisition time is greater than the spectrum length, which is driven by RBW, you can then move around and look at spectral content anywhere within that time domain acquisition. So I'm going to switch gears a little bit here and kind of show kind of a multi-domain example. I'm going to move a probe. I'm probing a number of different signals on the board. I'll kind of walk through each one here. Okay, so channel 1, which is up here, is just probing a simple little trigger pulse. You can think of it as an analog signal on the board. This trigger pulse, this is the scenario that I mentioned in the demo presentation slide where I've got a SPI bus controlled RF synthesizer. So I have one of those logic probes turned into channel 3. It's probing a 3-wire SPI bus here. I've got the clock, slave select, and master out, slave in here. The decode of this is being shown up over here in the decode table. We could also zoom in on that, of course. Channel 4 is the RF output of this signal, which is sitting at around 2.4 gigahertz. The spectral content of that is being shown over here in spectrum view. Okay, again, I can move my spectrum time around to kind of see what the spectrum is doing at different locations in time. Okay, so I can actually see the hop as I move through this. Okay, and then the actual SPI bus decode is actually showing up here. The codes that we're seeing in here, if I zoomed in on it, would be these same codes that I'm seeing right up here. I'm also probing the RF frequency versus time of the RF signal. That's right down here. Okay, so that's what I was triggering on in the previous example. And then channel 2 is actually probing the control voltage input to the VCO, or the output of the loop filter inside the PLL. Okay, and as you can see, these two, the frequency versus time and the VCO control voltage should match, and it looks like they do. And of course, you can even do things like take that frequency versus time trace, and I can drag it right on top of that channel 2. And if I play with my controls here, I can actually go line those two up to ensure that the frequency versus time characteristic of the RF and the VCO control voltage are indeed in lockstep, that there aren't any flat spots, there isn't any non-linearities going on, we're not hitting any limiting. So these are difficult measurements to make otherwise, but very, very easy to go do here. And I've got these little markers up on here that I can move around and place wherever I want to make a measurement to see what that frequency offset is or the VCO tune voltage is. I can move those around anywhere I'd like as well. All right, so this is one kind of a mixed domain example, analog, digital, and RF signals kind of all at the same time. Let's kind of go to switch gears to a multi-channel RF example. I've got an RF pulse coming into channel 1, shown up here in the top. Think of it as a radar pulse. In this case, it's a CW pulse at 3.85 megahertz, 3.85 gigahertz. Okay, and what I'm probing, what I've also got displayed up here is this next trace here is the phase versus time of that CW pulse. Now it might be tough to see. There's actually a flat line right here in the middle. If I go and turn the grid lines off here, then it might be easier to see. Okay, so basically this becomes my reference phase. So channel 1's phase versus time is set up to be the master phase reference. So all the other channels can be measured with respect to that one. So channel 2, I've got another copy of that 3.85 gigahertz CW radar pulse coming in, but that one is going through kind of a step phase change. And you can kind of see the phase versus time trace of that down here, where you can actually see the phase is actually changing with respect to this, channel 1 is steady, channel 2 is varying between one of 4 separate phases. Again, very tough to see that, but because we've got time correlated phase coherent digital down converters on every channel, we can actually see that phase relationship between these channels. And you could even do some kind of old school things here if you'd like. I could bring up like an XY plot and actually look at the phase change in the old school Lissajous type pattern as well. But being able to, and then we can kind of rearrange the way we want things to look, etc. But being able to look at phase versus time on multiple channels tuned to the same frequency can be handy maybe for MIMO applications or beam steering type applications to understand the phase relationships from through multiple tributaries. Okay, so again, you can do this across all 8 channels because all 8 channels are all phase coherent digital down converters. This is an example obviously where you're looking at the same center frequency on multiple channels. The next example I'm going to bring up here is going to be kind of a mixing example. So what I'm initially looking at here now in channel 1, this is a 200 megahertz wide linear frequency modulated pulse or 200 megahertz wide chirp, okay, centered at 1 gigahertz. I'm also displaying the magnitude versus time for that RF pulse. So it's just the RF magnitude versus time, and actually triggering on that. And it's also showing me the frequency deviation versus time. Okay, I've got a bunch of noise on either side of it, again, because this frequency deviation versus time is the first derivative of arctan of Q over I. And when the pulse isn't there, the I and Q data looks like noise. So that calculation looks like noise, but I can squelch that out if I want to. I can move the spectrum time and see how the spectrum of this LFM is varying across the pulse. So this is all going into a double balance mixer. The LO that I'm setting into the mixer is at 4 gigahertz. All right, and then the output of that mixer is coming in on channel 2. So let me bring up channel 2. So there's the output of that mixer on channel 2. If I go and turn on spectrum view for channel 2, all right, by default, channel 1 and channel 2 spectrum view are both at 1 gigahertz. So we can see that this signal is sitting at about minus 7 dBm going in, but the signal coming out is about minus 47 dBm, but that's at 1 gigahertz. So what we're looking at is the IF to RF isolation of this double balance mixer. So since my LO is at 4 gig, if I go into spectrum view and I unlock the center frequency across the channels, And let's set channel 2 to 5 gigahertz, right, which will be the sum of the IF and the LO. Right now I can see that's sitting at about minus 14.6, so about 7 dB of conversion gain or conversion loss. Okay, and now if I move my spectrum time back and forth, I can see they're obviously in lockstep. If I go into channel 2's spectrum view and turn on its frequency versus time, I can see it's obviously going to match, because we're doing a pure up conversion. I could turn on its magnitude versus time. In fact, if we take its magnitude versus time and put it on top of channel 1's magnitude versus time, it gives us the ability to compare the flatness of the input versus the output. All right. But I can go see that. Now, I don't have any filters in this system here, which means that in addition to getting the sum of the LF or the IF and the LO, I also get the difference. So if I change channel 2 to 3 gigahertz, right, that's going to be our difference frequency, right? So now I can see I've got the spectrally inverted version of the chirp. I can see my frequency versus time is going in the opposite direction. Okay, I can see I've got a little bit of a different frequency response out of that as well. And again, if I move my spectrum time, you can see now the spectrums move obviously in opposite directions because I'm doing that high side conversion and I'm seeing the inversion of that signal. So a pretty simple example of using multiple RF channels, and in this case at different center frequencies, to look at the frequency conversion characteristics of this particular mixer. Your needs may go beyond the basic vector signal analysis capability in the scope. Okay. And that's where we can then take our vector signal analysis software called SignalView PC, which is essentially the same user interface that you find on the real-time spectrum analyzers, but is also can be used with other instruments as well. You can run SignalView PC right on the scope. So this will give you the more in-depth vector signal analysis capability. It utilizes the digital downconverter's IQ data that's already being generated in the scope. And again, on the 6 series scope will give you up to 2 gigahertz of analysis bandwidth, and also the full vector signal analysis capability, looking at spectrums versus time, the typical basic amplitude frequency phase spectrograms, et cetera, versus time, but then add modulation analysis, pulse analysis, settling time analysis, all the more advanced features that you get along with a signal analyzer. So it really kind of gives you the best of both worlds because you still can retain use of the scope. So the scope controls all the triggering, so you can precisely trigger on the particular signals that you want to get, whether it's in the RF domain or triggering on a bus signal or triggering on something else to capture the event that you want, and then go analyze the RF portions of that event in the vector signal analysis software. You can have all these other analog, digital, and RF signals and channels all up at the same time, and then be able to see what I like to call the choreography of all the analog, digital, and RF signals simultaneously. So let's go do a couple of examples back on the scope here again. So I'm going to use this same scenario that I'm looking at here. So I'm going to just restore down the scope application. So this is all running on my scope. So I'm going to start up SignalView here in the background, running right on my scope. So so what I'll do is we know that our signal's at a center frequency of 1 gig. We want a 500 megahertz span to look at this 200 megahertz wide chirp. What I'll do is I go to connect and tell it to connect up to my scope. And I'll bring that up here. And if I don't make this big too, we can actually see both things happening at the same time. So I can see my scope and SignalView happening here. What I'm going to do is on the scope side of things, I'm going to go ahead and change my trigger to trigger on the RF magnitude versus time. Okay, so I'm triggering on the rising edge of my pulse here. I'll bring that down so you can actually see that. And now I can control other things from my scope as well. So if I adjust my reference level here, you can actually see it changes the magnitude of the signal that I see on the scope. Okay, see how it's going down, and going up. I can also go ahead and start changing how I'm acquiring data here. So let's bring up my time overview display. Here's the rising edge of my pulse. I can go grab some more data over time. And I can see how it's grabbing more of that data on the scope here. Right now, we can see my trigger point is sitting right at the 50% point. I can go into my acquisition controls here and say, okay, I want that trigger point to be, say, down at 20%. Okay. You can see how everything kind of works kind of lockstep here. And I can, finally control what I want to go look at here. Let's maximize signal view for now. And we can add all of our other displays. Some of the things that we saw in the scope, like a frequency versus time trace, right? There's my chirp. I can also start adding things that you don't have in the scope, like a spectrogram, for example, to look at spectrums over time. I can stretch that out to look at how that chirp spectrum is changing over time. In fact, if I right click and add a marker in here, I can move that marker around and you can see the red spectrum trace moving down in the lower right corner. And again, notice everything is all time correlated. Okay. But this is, again, your basic vector signal analysis, but we do have the ability of doing more advanced pulse analysis here as well. So I might minimize some of the displays I have up here because we can really fill this display up. But let's go to my pulsed RF analysis and let's add, say, a pulse table and a pulse trace. Maybe I'll go back and add, say, let's go back and just add that frequency versus time trace in again as well. All right. Now I'm going to go just make a couple of quick setting changes here. I'm going to tell it that I only want about a 500 megahertz acquisition bandwidth, so we don't just analyze more data than we need to. And I'm also going to tell it that I'm giving it a linear chirp, because this will allow me to do some more advanced measurements. Actually, let's go back to my pulse table here, and I can turn on, there's actually 32 different measured parameters on pulse signals that we can make automatically. So things like rise time, fall time, droop, ripple, repetition interval, as well as vector properties like pulse-to-pulse phase, frequency and phase deviation within pulses and things like that, and even some more advanced features. So the table will show me all those results. Some of these, like duty cycle, I don't know yet because I'm only capturing one pulse at this point yet, but we've got all these different measurements we can make. And you can also display any of those. Let's say I want to look at how the pulse width measurement is being made. I can actually see where that's being made. How is the rise time measurement being made? You can actually see where that measurement's being applied. So you can pick any measured parameter. For example, there's frequency deviation, right? There's my chirp. If I want to look at the phase deviation, we'd expect that when this is phase with respect to center frequency, so we expect that to be a parabolic phase shift versus frequency. Okay, and it is. Okay. We also can look at frequency and phase error. Since we told the instrument that we're giving it an LFM, we can actually look at the error from that perfect chirp. So we can see this is we're just seeing kind of the noise of that here now because it's really very close to a perfect chirp. And we could also look at the deviation from the ideal phase, right? That's the measured phase result. The deviation from that ideal parabola is that. So we can see that's down in the single digit degrees out of the 300,000 degree parabola that I had there. I didn't do anything to lock my references together here. And I know there's also some phase distortion in the way this waveform is created, but it's very small compared to this, again, this 300,000 degree parabola. Okay, we can go capture more pulses over time. So I just will grab a little more data over time here. So now I've got a number of pulses kind of stuck into memory here now. And so now my table is getting more populated with results from all of those. And again, if I want to pick any result to go look at, maybe I want to look at the rise time of pulse number 4, I just click on that cell and then that will bring up the rise time of that pulse. So it's and then you can literally walk up and down that. We can also do things like let's bring up, say, a pulse statistics plot here. The pulse statistics plot will allow me to look at any particular parameter, like say pulse width versus pulse number. I've only got 9 pulses in here, plus all the statistics of that. So it's like plotting a whole column of data out of that the table. And that can show as either a trend versus pulse number. You can show a time trend. So if you had a stagger of the PRI, you'd be able to measure that. And you could also do an FFT of that. Won't make a whole lot of sense here since we don't have a number of pulses, but this would allow you to pick up deterministic or frequency dependent or the spectral content of the variation of any measured parameter. And of course, you can also bring up a histogram as well for any of these measured parameters. This is all just part of what is naturally done in the real-time spectrum analyzers and vector signal analyzers, but now can be done on the scope itself. So I'm going to switch gears here a little bit and switch my signal generator to a different waveform. In this case, we'll look at a wideband modulated RF signal. This is a 2.6 gigahertz carrier modulated with a 1 gigasymbol per second 16 QAM signal. So let's change the center frequency to 2.6 gigahertz. And we'll start bumping my span up here. So let's see, looking at a 2 gigahertz span, now I can actually see the occupied bandwidth of that signal. And again, if we kind of somewhat minimize this, we can see that same thing, on the scope itself. So there's my actual RF waveform. There's in this case, the magnitude versus time, and then the spectral content is the same as what we're looking at here. But now if we want to go deeper and look at the modulation analysis of this, we can go to add displays, go to digital modulation. Let's add, say, a constellation diagram. Let's start with just that first till we get the modulation parameters set up. So I'll just go into the settings for the constellation. I like to put a couple more points per symbol to smooth out the trajectory lines between the I and Q.
Yeah.
This is a 16 QAM signal, so select 16 QAM and symbol rate of 1 gigasymbol per second. And there's my demodulated constellation diagram. Okay. I've got some pretty crappy cables going here, so the EVM isn't great, but 3% EVM on a 1 gigasymbol per second 16 QAM isn't horrible. We can optimize my signal level here. Okay. And then, of course, we can do other, look at some of the other modulation characteristics, such as EVM versus time, I diagram, symbol table, etc. As we add those displays in, just like all the other displays, everything is time correlated. So, for example, if I pause this for a moment, and let's right click and add a marker, that marker is now time correlated across all these displays. So if I start moving that marker around in time, so just kind of move them around here towards the beginning, we can actually watch that marker move in the EVM versus time through the constellation diagram over here. We can see it moving through the symbol table. All right, everything is all time correlated, because again, all this is just different math on that same set of IQ data. So again, another example of just being able to utilize the scope's wideband digital down converter for doing RF analysis.
Right.
So basically, we compare all these tools, right? Both Spectrum View and Signal View PC give you all your familiar spectrum analysis controls and spectrum analysis versus time and basic vector signal analysis capability. Spectrum View on the scope gives you multi-channel RF at the same or different frequencies, time correlation to analog, digital, and bus signals, RF triggering on magnitude or frequency versus time, and the measurements on the RF versus time traces, where Signal View PC is a single channel at a time, but with a more comprehensive RF analysis, spectrograms, IQ, the typical RF measurements, frequency phase settling, as well as detailed vector signal analysis. So what we're doing is essentially bringing the analysis features of the RSA to the scope platform. So if we compare those and say, well, the real-time spectrum analyzer, in contrast, is fully pre-selected, where the scope really is just a wideband front end. Okay, it does give you some real-time signal processing, real-time, millions of spectrums per second in that DPX display, as well as really powerful triggering capability to frequency mass trigger, DPX triggering, ability to do fast frame RF capture for low duty cycle acquisitions, and obviously very high dynamic range, 80 dB plus dynamic range with the signal analyzer. The scope and Signal View PC, on the other hand, gives you the multi-channel RF capability, channel to channel phase, different same center frequencies, really wide acquisition bandwidth, and this time correlated multiple domains. So they're really complementary tools from that standpoint.